My name is Emma Sieracki, and I will be explaining to you negative inducible control of the lac operon. The lac operon is a group of genes with a single promoter. It was first discovered in E. coli and involves genes that regulate its ability to metabolize lactose. These genes include the lacI regulatory gene that codes for the repressor, the lacP promoter, which binds to RNA polymerase to allow transcription, the lacZ gene that makes beta-galactosidase, the lacY gene that makes permease, and the lacO operator that interacts with the repressor. The lac operon is controlled through negative inducible control. This occurs when a regulatory repressor protein, such as the lac repressor, is normally bound to the operator, which prevents the transcription of the genes on the operon. If an inducer molecule is present, such as allolactose, it binds to the repressor and changes its conformation so that it is unable to bind to the operator. This allows for expression of the operon. When lactose is not present and there are no mutations, the repressor will bind to lacO. This binding prevents RNA polymerase from binding to the promoter because the operator overlaps it, thus preventing any of the lac genes from being transcribed. When lactose is present, some of it will be converted into allolactose, which binds to the repressor. This binding prevents the repressor from binding to the operator. RNA polymerase will then bind to the promoter region, and all of the lac genes will be transcribed. This results in beta-galactosidase and permease being made. Mutations in these genes will affect how they function. In the regulatory gene, I- is when the repressor can't bind to the operator. IS is when the repressor can't bind to allolactose. This superrepressor will result in it always being bound to the operator regardless of lactose presence, thus always preventing transcription of the lac genes. The regulatory genes are trans-acting, which means they can affect any element around them. The rest of the genes are cis-acting, which means they can only affect those next to them. OC is when the operator is always on and unable to bind to the repressor, regardless of lactose presence. P- is when the promoter can't bind to RNA polymerase. Lastly, there are structural gene mutations that will result in non-functional enzymes, which are also denoted with a minus. Even though lactose is present, the lacO gene is always on, and the normal repressor can bind allolactose, the defective promoter region prevents RNA polymerase from binding and transcribing the lac genes. The superrepressor, on the other half, can't bind to allolactose. This means it will bind lacO and prevent RNA polymerase from transcribing the lac genes. Thus, neither functional beta-galactosidase nor permease will be produced. If lactose is not present, the results will be the same. This is because both the super and normal repressors can bind lacO, thus preventing RNA polymerase from binding to the promoter and pushing transcription further. Hence, neither enzyme will be produced.